So I'm going to take a look at 3.5 to start off the week. And 3.5 is an extension of 3.4, applying all the things that we learned about how to find roots using synthetic division, graphing calculator, and rational root theorem. But now it applies to complex numbers. Okay, so when we do quadratic formula, when we're solving for roots, we may end up with square roots of negatives. So in the first half, we'll talk about how do you work with complex numbers, and then in the second half, we'll apply that to what we did in 3.4. All right, so just a couple reminders that if you have a number that is a zero of a function, a zero means you can plug it into your function, and the result comes out to 0. So if I had something like 3x minus 3, and that was my formula, I would say that the root of that is 1, because if I plug 1 in for x, it will result in 0. Okay, so 1 is the root. And if I were to graph that, it would cross the x-axis at 1, 0. So a root is a place where it crosses the x-axis. Now, if a polynomial never crosses the x-axis, okay, like if you had something like this, it doesn't mean that there aren't any roots. What it means is there are no real roots. So what happens there is when we graph it, we cannot get imaginary answers by looking at a graph. The only way to get imaginary answers to a problem about roots is to solve it algebraically. And most of the time, that means using quadratic formula. Okay, any question on that idea? And this is a polynomial. I'm not going to graph it on the calculator. I'll just sketch it by hand quickly. It's a parabola that's been shifted up 1. It's actually pretty much just what I drew up here. In fact, that's it. It's a parabola that's been shifted up 1. Now, if you shifted it down 1, then it would definitely cross the axis. Okay, we look more like that. By shifting it up 1, it will never cross. And if you just think about that from an arithmetic point of view, think about when you square a number. What kind of value do you always get when you square something? Yeah?
Positive.
You get a positive, or what's the lowest thing you could get if you square something? There's one number you could square and it doesn't come out positive. Yep?
Would it be 0?
0. But could you ever square a real number and get an answer that's negative? No. Because squaring means you're multiplying two things that are the same. Right? If you multiply a positive times a positive, you're going to get a positive. If you multiply a negative times a negative, you're going to get a positive. And the only other case in there is if you multiply 0 times 0, and then you get 0. So you're always going to get a positive, or you could get 0. And if you add 1 to a number that's positive or 0, you're never going to get 0. So we got to figure out how could we get a negative 1 right there. And we'll talk about that. So this is kind of the beginning of the review of imaginary numbers, complex numbers from Algebra 2. So what I have in that red box there, that is a definition. If you ask me why, well, there is no answer why. Why is I equal to the square root of negative 1? Because it is. It's kind of like asking in geometry, why do parallel lines never cross? That question can't be answered. They just don't. It's one of the, for geometry, that's one of the building blocks that parallel lines never cross. It's just like something that they start with, and they build off of that. Same thing here. This is something that they start with, and they build off of it. This you can't prove. This you can. We can definitely figure out what I squared is based off of this definition. So I squared means to take I and square it. Well, I is the square root of negative 1. And anyone think they know what you would get if you simplified the square root of negative 1 squared? Yeah.
Negative 1.
Negative 1. So look at what just happened. We just found something that you could raise to the second power, and the result came out negative. That would have come in handy in that other problem. Okay. So I squared is negative 1. So anytime you see an I squared in a problem, always change it to negative 1. So now, watch what happens if you plug I into the equation I had on the other page. What did you just say I squared is? Yeah. And what's negative 1 plus 1? 0. So we just found something that you can plug into an equation and the result comes out to 0. What does that mean that I is in this equation? It's a what of that equation? Yeah.
A root?
It's a root. It's something you can plug in for x and get 0 for y. So I is a root. And we're going to learn that where there's one imaginary root, there's always a second. Imaginary roots always come in pairs. And I'll show you that later on. Okay. So if you write down a complex number is generally in two parts. You put the real part first, and then it could be a plus or it could be a minus, it depends. And then the imaginary part. In my setup there, the real part is A, and the imaginary part is B. The I comes after the imaginary part to tell you what's in front of it is imaginary. Right, so these are all examples of complex numbers. That one and that one are what you call pure imaginary numbers. They have no real part. This one is called a real number. You could think of it as 4 plus 0i, no imaginary. And this is a complex number with a real part of 2 and an imaginary part of 3. And this is a complex number with a real part of 2/5 and an imaginary part of negative 1. That's what number is always in front of something if you don't see it. A 1 or a negative 1, it depends. If it's a minus sign, it's a negative 1 in front of I. Okay, so any questions on the difference between the real part and the imaginary part? So, when we write down an answer to a problem, that's what you generally want it to look like. Real part, plus or minus, imaginary part, and then an I next to that box. That's the format, okay, that you want to look for. All right, so let's talk a little bit about complex arithmetic. The first thing I want you to understand is that I in math is a number. And a lot of people get tripped up with that. Yes, I is a letter in the English alphabet, but in math, I stands for the number square root negative 1. Just like this is a letter in the Greek alphabet. But we would never use this as a variable in math because this already means something special. It means 3.14. 159, 26, 525, 8979, 323, 84, 6264, 3383, and it keeps going. But anyway, this is not a variable. So if you had to pick a variable to use in math, you'd never use the pi symbol because pi means 3.14. Just like in this section, don't ever pick I as a variable, because I stands for square root -1. It is a number. But if you think of the rules for combining like terms, like 3x plus 2x gives you 5x. If you think of I the same way, even though I is not a letter, but if you think of it like one, when you combine like terms, 3i plus 2i is 5i. It works kind of the same way. A lot of people don't, you're kind of like, well, what do you mean think of it as a number? You could put any number next to 3 and this formula would work. Like, say you had the number 6. 3 6s plus 2 6s is 5 6s, right? 3 of the 6s plus 2 more 6s is 5 6s. And if you do that out, that's 18 plus 12, which is 5 times 6. It's the same concept I'm doing here. 3 of the i's plus 2 of the i's gives me 5 of the i's, just like 5 of the 6's. It's the same exact concept. What else? When we multiply out complex numbers that have a real and an imaginary part, we're going to end up doing a double distributive property. Some people might have learned that as FOIL. When we divide complex numbers, it's kind of like dividing fractions. We don't really divide fractions, we multiply to divide fractions. And that's going to be kind of the same thing here. When we have to divide complex numbers, we're going to use multiplication, and we're going to use something called the conjugate. Right? And let's look at what happens with square roots. When we do quadratic formula, you're going to end up with a lot of problems today that have a square root and a negative number underneath. We never want to leave the negative under the square root. So what number is in front of x here? And include the minus sign with that number. Yep.
-1.
Right. It's like having a -1 times x. Everybody agree that -1 times x is negative x? Okay. And the rule for square roots is if you have a product of two numbers under the root, you can separate it into two roots. You can take the square root of the first number, the square root of the second number, and then multiply. But this is something special. What is the square root of -1? Yep. I. So, if you have to take the square root of a negative number, this is how you write the answer. The negative comes out as an I, and you're still left with the square root of x. Now, you might look and be like, well, wait, you just said we usually want to write it with the I after the number. Well, with square roots, that's kind of an exception. We put the I before the square root. Anybody know why I would do this? There's something kind of confusing about that. Yeah?
Because it might look like it's in the square root.
Right, that to me it kind of looks like, is the I under the square root? Is it not under the square root? It's confusing. Put the I in front of the square root, there's no confusion. Okay, so when you have square roots that you can't simplify, put the I in front. And when you have a fraction, we usually put the I right in the middle. Kind of like when you do y equals mx plus b. Or actually, you'd have a number there, something like 6. The variable usually goes right in the middle of the fraction. Could do this. Most people in Algebra 1 don't write it that way, even though it is the same thing. And we follow kind of the same pattern with imaginary. If you have an imaginary that's a fraction, put the I right in the middle of the fraction. After it. Okay. not before it. Okay, just a couple patterns we usually follow. So let's try these first two. Let's do the one on the right first. Square root of -7. Okay, anyone think they can tell me what that would be? Yes, Chris?
I square root of 7.
Yep, I square root of 7. So he followed that special case where we couldn't simplify the square root of 7, so we put the I in front. How about square root of -4? Zach?
2i.
2i. So that one's different because you can actually take the square root of -4, take the square root of 4, you get 2, and then the I comes out when we put the I after it, and there's no confusion because there's no root. So 2i. How about square root of -9? How about now? What would that one be?
I square root of 9.
And can you do anything with the square root of 9?
Oh, sorry. 3i.
Yeah. So we always want to simplify the square root as much as we can, whether it's a perfect square, or whether it's just a square root that you can simplify. So how about square root of -20? Anyone think they know what that one would be? Fully simplified. So if you get stuck, think of just, okay, how would you do square root of 20? And then think, okay, now I need to put an I on the outside. Yep.
2i times square root of 5.
2i square root of 5. Yep. So you can break 20 up into 2 root 5. So you can break -20 up into 2i root 5. Okay. And again, you'll see this happen when you do quadratic formula later on. Questions on that? All right, so let's take a look at adding. So to add two complex numbers, just think of it as combining like terms. You can combine reals with reals, and you can combine imaginaries with imaginaries. All right, so Casey, if I added these two together, what's the real part of my first number? Just the first number.
7.
7, and the real part of my second number? 4, and when you add the 7 and the 4, there you go, you get 11. And now do the same thing again. Real part here is -3. What was that, imaginary part? Imaginary part of the second one is 5. And then we combine -3 and 5. And Abigail, what would you get for an imaginary part? 2i. Okay, that's an example of adding complex numbers. Questions? All right, subtracting, kind of the same thing, but think of that subtraction as a distributive. You're subtracting 6 from the first part, and you're going to subtract the I from the first part. All right, so Tyler, what would I get for a real part?
For what?
For the real part.
2i?
That's imaginary.
Oh.
So I'm looking for the part without the I. -2. Yep. So -2. And how about, Ashley, what about my imaginary part?
Would it be -3i?
-3i. It's 2i minus I. So 2i minus another I minus 3i. Okay, any questions on that one? Generally, we don't see I squared come up with this. Multiplying, you will. And that's this one. Even if they didn't say multiply in the directions, how do you know that this is multiplication? Francesca?
Because there's no sign on the 3.
Yeah, they didn't put a plus sign or a minus sign, they just put two sets of parentheses, so you know it's multiply. And this is the double distributive property. So let's go through that. Bailey, what's 2 times 5?
10.
10. And 2 times negative I?
Negative
Negative 2I. All right. Jake, how about 5 times 3I?
15I.
15I. And 3I times negative I. Well, let's kind of break this part down. It's a positive times a negative, so what's that?
Negative.
That's a negative. Now I'm left with 3I times I. So what's going to go after the negative sign?
Would be 3I squared.
3I squared. Just like if it was 3x times x, you would write 3x squared. Same thing. 3I squared. Okay, so now we just have to combine some like terms and deal with that I squared. Francesco, what's negative 2I plus 15I?
13I.
So we get 13I minus 3 times I squared. But Matt, what did we say earlier I squared is?
Zero.
What did you say? 0? No, not 0. Let's go back to I. What was the definition for I?
-1.
For I or I squared?
I squared.
I squared is negative 1. Okay. Right, so Abigail, what's going to happen at the end there? Yep, and what will happen when we multiply negative 3 times negative 1? That's going to become a positive 3 at the end. Right, so it's 10 plus 13i, and you're subtracting a 3 times negative 1. That becomes addition. All right, and Jack, what would be my final answer?
13 plus 13.
Yeah, just a coincidence. They're both 13. That usually, they're not the same. And that's multiplication. Questions on that? All right. And the last thing we're going to look at is division. But I said earlier, when you have to divide, we really end up using multiplication again. But we end up multiplying by something special. They called the conjugate. So first, just explain what the conjugate is, and then I'm just going to have you guys I'll give you an example, and I'll have you tell me the conjugate. So the conjugate is when you negate the imaginary part. So the long way to say that is change the sign of the imaginary part. So if you started with something that was a plus bi, the conjugate would be a minus bi. If you started with a minus bi, the conjugate would be a plus bi. So let's try a couple examples. 3 plus 2i. Casey, could you tell me what the conjugate of that would be?
3 minus 2i.
Yes, 3 minus 2i. Okay, Ethan, how about 4 minus 5i? What would be the conjugate of that?
4 plus 5i.
4 plus 5i. And Chris, how about 3i?
It would be negative 3i.
Yep, negative 3i. And 6. I think they know the conjugate of 6. Jack? Not negative 6. I can see why you'd say negative 6. But in this case, it's not negative 6. Zach?
Just 6.
Just 6. Stays the same. And if you're thinking, well, how does that stay the same? Think of this as 6 plus 0i. Okay. The conjugate would be 6 minus 0i. Plus 0i minus 0i, same thing. Okay. Questions on how to find a conjugate? All right. So now, the last thing is, how do we divide two complex numbers? This is how you do it. You end up using multiplication, and you multiply the top and the bottom of your complex number, the top and the bottom, by the conjugate of what's in the bottom. So multiply the top and the bottom by the conjugate of what's in the bottom. All right, so let's see if we can write that out and then watch what happens. I like to put all the parentheses in because I know I'm going to have a lot of distributive. So I don't want to forget that. And anybody tell me, what am I going to multiply top and bottom by? Yes. Yes.
2 plus 3i.
2 plus 3i. Now let's do the bottom first, and I want you to kind of watch what happens here. Okay, when I look at the bottom, I already know that the answer is 13. Right? And there's a way I can do that very quickly without foiling, but let's foil and see if you notice the pattern. So let's start. What's 2 times 2? 4. And 2 times 3i? 6i. What's 2 times negative 3i?
Negative 6i.
Negative 6i. When you're doing the FOIL, that's how you think of it, the O and the I always cancel because they're conjugates. So you're going to get a plus something with an I minus something with the I. So those always cancel. And now, let's look at the part at the end. A negative times a positive is a negative. And what's 3i times 3i? Before we simplify it. Yep.
9i squared.
That's 9i squared. But I squared is what number? Yep.
-1.
Negative 1. So this is really 4 minus 9 times negative 1 is negative 9. So that's 4 minus minus 9. That becomes a plus 9. And 4 plus 9 is 13. So the way I did that in my head really quickly is I looked at this first number and I squared it. And I said, oh, that's 4. I looked at the second number and I squared it. And I said, oh, that's 9. And then I just did 4 plus 9. And if you think, well, should I square like the 3 or the negative 3? It doesn't matter. Because if you square 3, you get 9. If you square negative 3, you get 9. So all you have to do is square the first number, square the second number, ignore the I, and then add them up. If that trick is confusing, you don't have to do it. Just FOIL it every time. But you'll be doing some work you're going to cross out. So. All right, so the bottom is 13. And the top, we don't really have a trick for that. We just have to do it up. All right, so we'll start with 5 times 2. Francesca, what's that give me? 10. And Matt, 5 times 3i?
15i.
Plus 2i.
17.
17.
I.
And what comes after it?
I.
I, yep, good. So we get 15I plus 2I is 17I. And Abigail, what's I? Positive I times positive 3I. Sorry, can you say it again? Good, 3I squared. Let's write up above what 3I squared really is. Jack, what does 3 times I squared come out to?
-3.
Right, so this is really a -3. And when we combine that with a 10, 10 and minus 3 gives me 7 plus 17I over 13. Now, we're pretty much done. The only thing is that answer written like that is not this. You don't have a real part and an imaginary part separate. You've got one big fraction. So, we want to separate that into 2 parts. Anybody have a guess what the real part is going to be in that problem? As a fraction. Yep.
7/13.
7/13, yep. And anyone have a guess what the imaginary part is going to be? How about Casey? 17 divided by what? 13, yes. Good. 17 divided by 13. And that is how you want to write your final answer. Okay, so that reviews complex numbers. Add, subtract, multiply, and divide. Any questions on that review? All right, so now we're going to try a few problems that go back to what we did in 3.4, setting an equation equal to 0, finding the roots. Except now, keep in mind, roots can be imagined. Okay. All right. So whenever we have to solve a polynomial, what's the highest degree polynomial that we like to work with? We don't want it really any higher than this, because then it gets a little bit more complicated. But at least if it's this degree or lower, we know how to solve it. So what degree do we really want to have at the worst here? What's the highest degree we want to have, and it's still a pretty easy problem? Yeah?
Would be 3.
I can't really solve a degree 3 quickly unless very special things happen. So if I give you degree 3, special things would happen. But it's still going to take a lot longer because you're going to have to do rational root theorem. Then you're going to have to use synthetic division. And then from there, you're going to have to use your graphing calculator. So degree 3 is going to take a while. Yep?
So it'd just be like 2.
Why? Why is a degree 2 pretty quick to solve? Anyone tell me what makes a degree 2 pretty straightforward to solve? Easy. I mean, we've been solving these since algebra 1, right? These are degree 2. How do you solve a degree 2? What if you can't?
Quadratic formula.
Quadratic formula. Okay, that's what makes degree 2 easy. We have a formula for it. We just have to plug in, and we're done. So in this case, Chris, what's A?
That would be 1.
And Zach, B?
1.
And C, Tyler? 1. So we're just going to fill into quadratic formula and see what we got. Ashley, can you start us off with quadratic formula using these values?
It would be -1
Yep, so negative 1 because we're negative b, yep.
Plus or minus the square root of 1 squared
So b squared, yep.
minus 4, and then AC.
Yep, 4ac, which is just 1 and 1. And Bailey, what are we going to divide all that by?
2, 5,
Yeah, it's divided by 2a, which in this case would be
4.
1. All right, let's clean that up and get our answers. Notice here we have a plus or a minus, which means you're going to get 2 answers, and the highest exponent is a 2. You always get as many answers as the highest exponent. Okay. All right, so negative 1 plus or minus square root of, what am I going to get under the root when I simplify what's there? Chris?
-3.
Good, negative 3 over 1. Now, we talked about the square root of negative 3. We don't want to leave the negative under the root. I don't really need to keep putting it over, oh, I'm sorry, this was over 2. I was going to say, if it was a 1, I don't need to keep putting it over 1, but it was 2 times 1, which is 2. So at least we caught that before we finish the whole thing. And what's the square root of negative 3? This was one of the first things we practiced with imaginaries. Sarah?
I square root.
Good. I square root 3. So that's perfectly fine. You can leave your answer like that. If they said to write it in standard form, your real part is negative 1/2, and your imaginary part is root 3 over 2. I. Either way, that's the same answer. Notice here it's a fraction, and I put the I in the middle, and I mentioned a little bit about that earlier. Okay, and we're done. Questions on this one? Any part of what we did? All right, let's look at these two answers again. Negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. Those two numbers are what? We called those something earlier. Yeah? They're what? They're the roots, and they're complex, but specifically negative 1/2 plus root 3 over 2i and negative 1/2 minus root 3 over 2i. How do those numbers compare to each other? They're what?
Conjugates.
They're conjugates. So when you're finding roots and you get an imaginary answer, I said they always come in pairs. More specifically, they always come in conjugate pairs. So what that means is if they tell you in a problem, 2 plus I is a root. Well, they're not telling you the whole thing. If 2 plus I is a root, 2 minus I is a root. They always occur in pairs. You can never have an odd amount of complex roots. It has to be even. Now, of course, if the imaginary part is 0, then now you're dealing with real numbers. That's more like what we did at 3.4. For this trick to work, you have to have an imaginary part of the number that's not 0. Now, this last thing at the bottom, I'm just reminding you that all the things we learned last week, remainder theorem, synthetic division, factor theorem, Those all work with complex numbers. And we're going to try one with synthetic division. I'm not going to have you do long division with complex numbers. We'll stick to synthetic. So just as kind of I know we reviewed synthetic division a little bit, but if I said to you, show me that 3 is a root, what number would go on the outside right here when we do the synthetic division? Tyler?
3.
3, yeah. You just put the number on the outside that you want to show as a root. That's all. I want you to show me that 1 minus 2i is a 0. Is a 0 the same as a root? Yeah. Thank you. So 1 minus 2i is going to go on the outside. And what are going to be my numbers on the inside? Yeah.
1, 0, 1, 10.
Yep. Now this is probably as bad of a problem as I would give you, because if it gets any higher than degree 3, it starts to take a really long time to do all the multiplication. Okay, so this one won't be too bad. We're going to have to end up doing foiling twice. Okay, but that I think will be it. Okay, bring down the 1. That's your first step. Now, multiply 1 minus 2i times 1. Everything is distributive. What's 1 minus 2i times 1? Yeah.
1 minus 2i.
Just 1 minus 2i. Now, add in your column, what's 1 minus 2i plus 0? Yep.
1 minus 2.
All right, so really they've gone pretty easy on us so far. We've had really nice numbers. It's going to get a little bit harder for the last 2 steps. And remember, we're hoping for a remainder of what? Yeah. Yep, we're hoping to get 0 if this works. Now, you're going to multiply 1 minus 2i times 1 minus 2i. I'm going to do that off to the side so I can keep the synthetic division nice and organized. All right, so let's do this. Francesca, what's 1 times 1?
1.
And 1 minus 2i?
1i. Or I.
So we have, first of all, positive times negative.
Wait, what?
What's positive times negative?
Negative?
Negative. And now it's just 1 times 2i.
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 Oh, times. Oh,
Yep.
I know.
And then another 1 minus 2i. So that's another minus 2i. Negative 2i times negative 2i. Now, what's that going to be?
Wouldn't that just be 2i squared?
Well, you're multiplying. So negative 2 times negative 2.
2i. Oh, sorry, 4i.
Like that?
Yes.
We need something else there. Yep.
Squared.
Square.
Squared. And 4i squared is really what number? How about Abigail? Which is? So we got a negative 4 and a positive 1. That's a negative 3. And Jack, what's negative 2i minus 2i?
Negative 4i.
Negative 4i. Now let's add that up. There's nothing to combine with the imaginary. There never is. And Casey, what's 1 plus negative 3? Sorry, go ahead again. -2. And now I'm at my last step. Chris, what am I multiplying in the last step?
You're gonna be multiplying -2, or, -2 minus 4i by I minus 2i.
By 1 minus 2i. Okay, let's do that out and see what happens. Zach, 1 times -2?
-2.
-2. And Tyler, 1 times -4i? -4i. And Sarah, -2i times -2?
Positive 4i.
Positive 4i. And Jake, -2i times -4i.
8i.
That's 8i squared. What's going to happen when I combine like terms there, Bailey?
-4i cancel.
Yep, those are gone. So -4i plus 4i. And remember, I squared is -1. -1 times 8, Ashley? -8. And Francesca, what's -2 minus 8?
2 minus 8. 6.
That would be -2 plus 8.
Oh, -2 minus 8. -10.
-10. And we get exactly what we expected, a remainder of 0. Right. So this synthetic division kind of combines usually 2 foiling problems into one. All right. But the foiling I do off to the side. Okay. Any question on doing synthetic division? Now you might look at that and say, boy, that's quite the quotient right there. We would never really do anything further with this kind of problem. Okay, because when we have quotients with imaginary numbers for coefficients, that gets weird. So all you'd have to do is what we did right there. That's it. All right, so that was that. Let's try that. All right, let's think about this one for a second. Odd degree polynomials, like x cubed, x to the 5th, things like that, are always going to have at least one real 0. What did I say earlier about real zeros when you look at them on a graph? They're the what of your graph? Yep.
Root.
They're the roots algebraically, but how about visually? What are they on the graph itself? Yep.
The x-intercept.
They're the x-intercepts. So another way for me to ask this question is, why do odd degree polynomials always cross the x-axis at least one time? Anybody remember why odd degree polynomials have to cross one time? Evens don't. Think of a parabola. I can definitely draw a parabola that never crosses the x-axis. Yep.
Because it's either line, it's a line. It swerves down. It's going up and down.
So if you look at the end behavior of a cubic, one end is up, one end is down, and they're continuous, meaning you never lift your pencil when you draw them. So if you go up and down forever, and you never lift your pencil in that whole time, you're going to go through 0 at some point. So that's why odd degree polynomials will always have at least one real root. So the cases you could have, let's say for third degree, in terms of real and imaginary solutions, you could have 3 real, no imaginary. That would look like this when you draw it. It's 3 separate reals. This is also 3 real. You might say, huh? How's that 3 real? This is what we call a repeated root. And I think we've talked about that. So that's a repeated root. So there's 1, 2, And that's 3. So that still is the same case. 3 real, no imaginary. Could you have 2 real, 1 imaginary? Is that possible? Two real, 1 imaginary. Yep.
Yeah.
What did we say about imaginary roots?
They don't touch the x-axis.
Okay, you can't see them visually. We said that. What else did we say about them? Right after we did the quadratic formula problem. Yeah?
There's 2 of them.
They always occur in pairs. So, is that possible? No. You have to get 3 solutions, but there's no way you could have 2 real and 1 imaginary. Impossible. How about 1 real, 2 imaginary? Is that possible? Sure. Yep. You definitely have that, because that's a pair. Could you have no real and all imaginary? No, we just said that odd degrees have to have 1 real all the time, so you can't have 0. So that's impossible. So when you're solving a 3rd degree problem, it always is going to be one of these 2 cases. 3 real, no imaginary, or 1 real, 2 imaginary. All right, let's look at this one. Now, I don't like this one as much as the first one we did. What do you think I don't like about this problem? Makes it a little bit harder. Yeah.
It doesn't have an x squared or x.
Okay, well, if I had something like this, just like y equals, or let's say even something simpler, like f of x equals x squared plus 2. That's not bad to solve, even though it has an x squared. So whether you had an x squared in this one or not, it wouldn't make it necessarily easier or harder. There's something else that's already in it that makes it harder. Anyone think they know what's making it harder, Casey?
That it's x cubed.
The x cubed, right? We don't have a cubic formula that we know. So I cannot plug this into quadratic right away. I have to get the cubic down to a quadratic. And how do we get something from a cubic down to a quadratic? What do we have to use to do that? So what did we do in 3.4 when you had a cubic and you had to solve it? You can't plug it into quadratic formula till you get it to a quadratic. But what's the thing we do that brings the exponent down 1 degree? Yep. We have to do synthetic division, and how do we find the number to use in synthetic division? I don't just want to sit here and start guessing every number I can think of. That's going to take a long time. So how do we get a list of possible numbers? Yep.
Have to use rational root theorem.
We have to use the rational root theorem. Now I can already tell the answer is 1. Just because it's not that hard of a problem to look at and say, oh, 1 to the 3rd power minus 1 is 0. But let's pretend that it wasn't as easy as just looking at it and guessing that 1 works. So let's start with P and Q. P would be the factors of -1, which are plus or minus 1. And Q would be the factors of the coefficient of x cubed, which is 1. And how about, Ethan, what are my factors of 1?
1.
And
-1.
-1. So when I write all my P over Q's, Francesca, what are all the different P over Q's I could have?
1.
And?
-1.
Yeah, so my possible roots well, I should say rational roots, are 1 and -1. Now, that's such a small list, and this formula is so easy to plug into, we can plug these numbers in pretty quick and check which one works. What if you had like 20 numbers? How would you narrow down the list quicker than trying every one of them? That's going to take forever. Francesca?
Don't you graph it and see what it hits?
Yeah.
Is it-
Yeah, you graph it and see which ones look close and then try that one. Okay, but I can tell just by plugging in +1, 1 cubed is 1, -1 is 0. Okay, we just found a root. So we've got 1. And now we have to do what Sarah said. We have to divide through synthetically by 1. Not really interested in the remainder. Since 1 is a root, I already know the remainder is going to come out to what? Yeah. Is it Jake?
0.
It's going to come out to 0. I'm interested in the quotient. I need the quotient, and then I can solve that. And the quotient is going to be 1 degree smaller than that number, which is perfect, because then that's a quadratic. So we've got 1, 0, 0, -1. Okay. Bring down the 1. Multiply. 1 times 1 is 1. Add it to the 0. 1 times 1 is 1. Add it to the 0. And technically I'm done. That's my quotient. If you want to finish it and get the remainder, there you go. So, now, if I write this as an equation, what does that mean?
That's my quote. My quotient.
Yep, can you write it out for me?
Oh, x squared plus x plus 1.
And we're setting it equal to what? To solve.
X cubed minus 1.
Well, we're trying to find the, what are we trying to find here? In this, we want to know
The other roots.
the other roots, so we would have to set it equal to,
X minus 1.
um,
Oh, 0. Sorry.
0, yeah. If you're finding the roots, you always want to set it equal to 0. Now, look at this equation. X squared plus x plus 1. X squared plus x plus 1.
Varsity girls soccer should be good, thank you.
So that quotient that we just ended up with, we've already solved that problem. Example 4. So I'm not going to go back and do it again, but the other two answers that you get are -1/2 plus or minus √3/2i. So we'll go back here. And the video, I'll put the video online later. This is the last example.
Okay, thank you.
So see example 4 for how to solve that. Now I forgot what the roots were. I think, was it -1/2 plus or minus √3/2i?
Yeah.
Okay. And what's kind of annoying is if they ask you in a problem to find just the imaginary roots and they don't care about the real ones, you can't do that. If you want the imaginary roots, you have to find the real ones first. So you might think, oh, they're not having me find the real ones. It saves me some time. Not really. Because you have to do the synthetic division because the graphing calculator can't give you the imaginary roots. So notice in this problem, highest exponent was a 3. 1, 2, 3 answers. Highest exponent in this problem was a 2. 1, 2 answers. In fact, that will always happen. The number of zeros, or the number of answers that you get, is always equal to the highest exponent. It could be a combination of real and imaginary, but together, they always have to add up to the highest exponent. And what that means is, since the number of roots in a problem is always the same as the number of factors, we can write that down as a theorem. If you have a polynomial and the degree is greater than 0, and you have real coefficients, like that. There's a polynomial with a degree 3, and all the coefficients are real, 1, -7, -6. You will always be able to take that and factor it into n factors. So just like a quadratic has a highest exponent of 2, and when you factor it, it's 2 sets of parentheses. How many sets of parentheses do you think I would need when I factor this one completely, based on that theorem? Yeah, 3. Okay. It says that if you have a polynomial with a degree greater than 0, then it will factor into as many factors as the degree. That's what that says. So this would be fully factorable as that. And at this point, you guys should be able to do that. Because these are all nice answers, that's why. So you'd have to use rational root theorem, find one of the roots, and then when you do synthetic division, the quadratic formula would give you the other 2. Or actually, because they come out nice, you could factor. Now, the roots don't need to be distinct, right? Like this. If I were to graph this on the calculator, or if I were to multiply all that out, the highest degree term would be x to the 5th. And there are 5 roots. -1, -1, 2, 2, and 2. That's 5 answers. They're not all different answers. They're repeated. And what we call that is multiplicity. Multiplicity means that you have a root that repeated itself. -1 is a root that occurs twice, and 2 is a root that occurs 3 times. That's what multiplicity means. So tonight, there'll be, part of the homework will be, like the first half, will just be practicing complex number arithmetic. Not every problem is like a synthetic division. A lot of them are just like what we did in the first half. I think up to number 22, I want to say is complex arithmetic. And then 25 to 40, those are the ones we did in the second half. But there's not as many of those. Okay, so it's on 193. We'll take a look at that first thing tomorrow. And again, reminder, I will be after school on Thursday if anybody needs to stay. Otherwise, you're welcome to come any period 1, 4, or 9 if you need to come see me or finish something up.